Welcome back, kids. This is Stoichiometry Notes. We're going to do numbers 12, 13, 14, and 15, and there's no 13, so we only have 3 problems. In this math problem, you have a gigantic number of zinc atoms that you're going to put into something that's on table K. It's an acid. This acid happens to be called phosphoric acid. It's got 3 hydrogen ions and a phosphate. It's aqueous. Zinc atoms are solid. Doesn't say solid, but it should. Zinc solid in aqueous solution is the setup for a single replacement reaction. Zinc is higher than hydrogen. Zinc replaces hydrogen in the solution, and hydrogen gas pops out as it precipitates, but it's a gas, so it doesn't really precipitate. It turns into bubbles and disappears. Now we're going to balance this equation. We're going to start with 1 zinc in the front, but there's 3 in the back, so I'm going to start by putting a 3 right here. There are 3 hydrogens in the front, but there's 2 hydrogens in the back. 3 and 2 are odd and even. The only way to fix that is to double the odd one, so I'm going to turn this into a 2. I have to start over. 3 zincs, so far so good. 6 hydrogens now in the front. I have to put a 3 here. So now let's start over again and see what's going on. 3 zincs. We have 6 hydrogens, and in the front I have 2 phosphates, and look in the back, here are 2 phosphates. This is going to be in a 3 to 2 to 1 to 3 ratio. John Dalton's happy, I'm happy, and I hope you're happy too. So we'll clear the drawings and we'll move to the next slide. And we have a 3 to 2 to 1 to 3 ratio. Now we're starting out in this crazy big stoichiometry problem with particles. We're starting out on particle island, on the left side, particle island 1, and we want to get to grams island number 2. So in order to do this, we're going to do 3 steps. The first step is to turn this gigantic number of atoms into moles. Now to go from particle island to mole island, you have to remember that 1 mole of any substance, atoms, in this case 1 mole of zinc atoms, is Avogadro's number. So in order to convert these atoms into moles, we have this starting point over 1, and then we have 1 mole of zinc over Avogadro's number of atoms of zinc, and the atoms in the numerator and the atoms in the denominator cancel. The math is going to work out to in 2 parts, 4.56 divided by 6.02, and then 10 to the 25th divided by 10 to the 23rd. Now when you divide this, 4.56 divided by 6.02, you're actually going to get in your calculator 0.757, but then 10 to the 25th divided by 10 to the 23rd is 10 squared, or 100. So this crazy large number of atoms is really 75.7 moles of zinc. A different way to say this number of atoms is to just call it 75.7 moles of zinc. Now, that's part 1. Now, in order to get across the tunnel, we have to do what's called the mole ratio. Now, the mole ratio, even though there's 4 parts to this equation, we're only looking at 2 parts. We're looking at the part called zinc and the part called hydrogen. The zinc and the hydrogen happen to be in a 3 to 3 ratio. How cool is that? That actually makes this a little easier for us. So we write MR for mole ratio. We're looking at zinc and hydrogen. It happens to be in a 3 to 3 ratio. Now, I suppose you could think, hey, I'll just reduce that to 1 and 1. Never change the mole ratio. The mole ratio here is 3 to 2 to 1 to 3. We happen to be looking at 3 to 3. Leave it alone. Now, we have not 3 moles of zinc. We have 75.7 moles of zinc. And we want to know how many moles of hydrogen is that proportional to, so the X goes on the bottom here. How do you deal with this? You have to cross multiply, and that's going to be 3x equals whatever that is, but basically X is the same, 75.7 moles of hydrogen. So we started out with atoms, we switched to moles, we did the mole ratio, and now we know that when this reaction happens perfectly with 75.7 moles of zinc, we're going to get 75.7 moles of hydrogen. Now, how many grams of hydrogen is that? Well, to go from mole island 2 to mass island 2, we have to use that conversion factor of 1 mole equals the molar mass. And the molar mass of hydrogen is 2 grams per mole. So we move the 75.7 moles of hydrogen over 1. We're going to multiply it now by the molar mass which is 2 grams of hydrogen. It's a Hunkelbrief twin H2. And when we cancel out the moles, we get exactly with 3 significant figures, 151 grams of hydrogen. Now, what really just happened? In this reaction, you have a big pot of phosphoric acid. You have a whole bunch of zinc. You put the zinc in and hydrogen gas comes out. Zinc phosphate forms in solution. Now, if you had exactly that many atoms, 4.56 times 10 to the 25th atoms of zinc, if you could measure them. Well, another way to say that is 75.7 moles. If you put that much zinc into acid, you're going to get exactly 75.7 moles of hydrogen to come out on the other side. The reaction's perfect. To the atom, it's perfect. And then the question is really, if that much hydrogen comes out, what does it weigh? What's the mass of it? Well, that many moles of hydrogen is going to weigh this. So basically, we said if you could count to this crazy number of atoms and run it through phosphoric acid, that much zinc is going to give you this many grams of hydrogen. This, honestly, is one of the hardest stoichiometry problems there is. It is 3 steps, but whenever you have the particles, we have exponents, the math, the numbers can get bigger. But this is it. This is, if you could follow this, and you should probably do this problem again, right? Just hit pause, go back in the slides, do this problem again on a piece of white paper, and make sure you get the right. The answer is 151. Remind yourself, it's 151. Do it again. Make sure you can do it. Follow the steps. Okay. That's an extra slide. Well, we skipped one, and now we're up to 14. In this reaction, we have hydrogen and nitrogen that are going to make ammonia. They're going to synthesize together, and there's a balanced chemical equation here. We have 3 moles of hydrogen and 1 mole of nitrogen, going to make 2 moles of ammonia. Now, this question says, how many liters of nitrogen would be required to react with exactly 809 liters of hydrogen when ammonia forms? Now, it doesn't really matter about how much ammonia forms. The exact proper amount will form. This is a stoichiometry problem. We're only looking at 2 parts, and in this case, we're looking at hydrogen and nitrogen. So the question is, where are we starting, right? The sentence starts out with liters of nitrogen as a question, but we're starting with 809 liters of hydrogen. We have to first convert that into moles. We're going to compare the moles of hydrogen to the moles of nitrogen, and then we're going to convert that many moles of nitrogen into liters again. It's a 3-step problem, from liters island to moles island to moles 2 island, and then back to liters or volume 2 island. So here we go. The first thing we're going to do, we have 809 liters of hydrogen, and we have to convert that into moles. And 1 mole of any gas is 22.4 liters of that gas. So we have liters in the numerator, we put liters in the denominator. It's a division problem. 809 liters, which is a pretty big balloon. Another name for that is 36.1 moles of hydrogen. Now we have to do what's called the mole ratio between hydrogen and nitrogen. Now, in this particular setup here in black, I put the nitrogen on the top. You can put the hydrogen on the top or the nitrogen. The top and the bottom, the numerator and denominator, in a sense, don't matter, as long as all the nitrogen numbers are always in the numerator, or all the nitrogen numbers are always in the denominator. We write nitrogen and hydrogen so we keep the numbers consistent, and we don't do this. We don't flip over a fraction and do things upside down. In this problem, in this equation, there's 1 mole of nitrogen for every 3 moles of hydrogen. Now, nitrogen's in the top. I could have done the whole thing upside down. Mathematically, once we cross multiply, we get the same answer. But we have 1 mole of nitrogen is in proportion to 3 moles of hydrogen. That's from the balanced chemical equation. Now, we don't have 3 moles of hydrogen. We happen to have 36.1. The question is, how many moles of nitrogen are we going to get? If it's in a 1-to-3 ratio, it's going to be x to 36.1. Now we have to cross multiply and divide to figure out how many moles of nitrogen are in proportion here. So we multiply 3x is going to equal 36.1. We divide both sides by 3. And with the decimal, it rounds to just 12.0 moles of nitrogen. That's a little bit rough, but that's the math, and that's the significant figures. So if you have 809 liters of hydrogen, which is really big, and you react it with sufficient nitrogen, mathematically, you're going to need 12 moles of nitrogen to deal with that. But the question is, how many liters of nitrogen? How big a balloon is that 12 moles? Now we have to take, for the 3rd step, the moles of nitrogen, and we have to switch that or convert that into liters. So we're going to move the 12.0 moles of nitrogen over 1. That's going to be our new starting point. We're going to multiply that by the factor of 22.4 liters is a mole. Now, in this case, look at this purple conversion factor compared to the red one. The red one has the moles on top, and this purple one has the moles on the bottom. Why? Well, we're starting in the purple third part with moles in the numerator, so we have to cancel them by putting moles in the denominator. Plus, once they cancel, the answer will come out in liters. That's what the question is, how many liters? So the moles will cancel, and mathematically, this works out to this number, 269 liters of nitrogen gas. But what does this mean? If you have a really big balloon of 809 liters of hydrogen, how many liters of nitrogen will it take to perfectly balance this equation? Well, it's going to take a big balloon, but it's only going to be 269 liters. It's going to be, well, looks to be about a third, right? Looks to be about a third. Give or take with the significant figures. All right, this is the last problem we're going to do in this set, and then we'll do one more slideshow, and we'll be done with stoichiometry. You just get a whole bunch of homeworks done. All right, quick reminder, make sure this week before the holiday break, you pick up all the notes, because when we come back online, I suppose most of us in January, we're going to start the next topic called phases. It's all printed, and as of Monday, it's going to be available at school. You need to pick that stuff up so you have it ready to go for the first day of 2021. All right, last problem. In this problem, C2H6 is balanced. It's called ethane. It's going to combust with oxygen. It's going to turn to carbon dioxide and water. This is combustion. It's already balanced in a 2:7 to 4:6 ratio. All right. Now, what happens if we start out with 15.6 moles of ethane? How many moles of oxygen are going to be used? Now, this actually is the easiest stoichiometry problem so far of the year. This is a moles to moles problem. There's very little math. In fact, it's only one step. It's practically already done, right? In this problem, we have a mole ratio of ethane to oxygen, which is 2:7, right? Look at the top, the balanced equation. There's 2 moles of ethane requires 7 moles of oxygen. So it's in a 2 moles to 7 moles ratio, ethane to oxygen. We keep the 2 with the ethane on the top. Now, what if we had 15.6 moles of ethane? Because the chemistry class, you got to do some math. It's a silly number, really. Well, if it's in a 2:7, it's got to stay proportional to 15.6 to I don't know what. But because it's an equality, you can cross multiply and solve for the answer. So the answer here, mathematically, we're going to multiply. It's 2x is 109.2. We divide both sides by 2 to get x equals 54.6 moles of oxygen. What this means is, in this balanced equation, 2 moles of ethane require 7 moles of oxygen. Now, if it was 4 moles of ethane, it would be 14 moles of oxygen. But we have a crazy number, 15.6. That proportion, 2:7, 4 to 14, is equal to 15.6 to 54.6. The answer is 54.6 moles of oxygen. This is a moles to moles problem, right through the tunnel, one step, bada bing, bada boom, you're done. All right? We have one more slideshow. We're nearly done with stoichiometry. None of this is hard. It's all mole math, mole math, mole math, and then these simple proportions that come directly out of the balanced chemical equation. All right. Thanks for playing. We're going to end this.